Recall that the variance of a random variable measures the average distance of the random variable from its mean mu squared. In particular, we have a formula for variance. Also, recall that standard deviation is a more useful quantity. It is the square root of the variance. However, for now we will focus on variance. Computing variance is the first step to computing standard deviation, and computing standard deviation is simple from it. You just square root your answer. Now let's do our first calculation of variance. Consider a random variable x which has non-zero probability at 4 points. In particular, the PDF is given as follows. My goal is to calculate variance. However, if you look at the variance formula, it depends on knowledge of the mean mu, or expectation E of x. So I start by computing the expected value of x. Here's the formula for expected value. Then, I work my way through the 4 cases that have non-zero probability. Each time I have the PDF add a value like -2, multiplied by the number -2 in this case. Plug in the values from the PDF, and we find that the mean or expected value is -0.7. Now it's possible to compute the variance. The formula looks almost the same. I've highlighted in blue here the only places where anything changed. The k term got replaced by k minus the mean squared, where the mean was the expected value of -0.7. And then moving down to where I multiply the PDF times the value of k, I've replaced that with k minus -0.7. Finally, you find that the variance is 1.31. Notice that the method we've been using applies to more general functions. For example, if I wanted to compute the expected value of x squared, I would take the same formula that I just saw for the mean and the variance, and the only change would be that instead of multiplying by k, or by k minus mu squared, I multiply by k squared for the expected value of a square. Again, blue shows the only parts that are changing, and you find that the expected value of x squared is 1.8. I picked the example of a square for a reason here. Let's review the 3 numbers that we've seen so far. The mean was -0.7, the variance was 1.31, the expected value of the square was 1.8. Notice that if you take the square, 1.8, and you subtract the square of -0.7, you get an answer which actually matches up with variance. This is not a coincidence. We're going to come back to this at a later point. For now, though, just take this as a theorem to be proven later. So when you need to calculate variance, you can either use the definition, which is the expected value of x minus its mean squared, or you can compute the expected value of the square, the expected value of x, and work with that. In the current discrete setting, there is not a significant difference in difficulty between those. When you learn about continuous random variables, however, it will be significantly different. But just to refresh in the discrete setting, let's recompute the quantities in question. The mean was found as follows. To take the mean of the square, all that needs to change is to put a square on everything. So almost identical. Once you found the mean, put a bunch of squares, you have the square term. Then you plug that in, 1.8 from the square minus the mean squared, and you have the variance. So we see that even in the discrete setting, this is a bit simpler to calculate.